we're going to begin talking about our series work. What's going to happen here over the series of the next several lessons is we're going to talk about approximating functions with certain types of other functions. And then we're going to leave that completely and we're going to start talking about sequences and numerical series and tests for convergence and divergence. And we're going to work on that for so long you're going to wonder, what on earth does this have to do with the first couple of lessons where we talked about building polynomials and approximating other functions. So just bear with me, and by the time we get through all this, you'll see how they all tie in together. All of this information is on the BC exam in May, and what you need to know is of the 100% of information on the BC exam, 40% of it is Calc 2 information. Everything that we've done beyond our lesson on volumes by cross-sections has been Calc 2 information. A few of the things we did in the fall were Calc 2 information. But 40% of the BC exam is this Calc 2 stuff, and easily half of that 40%, a full 20% of your BC exam, is on series. So it's my opinion that unless you have a good handle on series, you're not going to make a 5 on the BC exam. There's just too much of it on the test. We know for absolutely certain that we're going to have a free response question that covers series on the BC exam. So there's 9 out of 54 possible points on the free response. So we're going to have a good handle on this. So work through this with me. There's a lot of information to cover, but we'll cover it completely and thoroughly, and we'll have enough practice that you'll be really comfortable with it by the time the BC exam comes along. So, function approximation. Well, there are two ways to approximate functions. We can use a function to approximate, so approximation by functions, and approximation of functions. Well, you say if we have a function, why do we need another function to approximate it? Well, maybe it's a really ugly looking function. Maybe it looks something, I don't know, like the tangent inverse of e to the cosine inverse of 3 to the e to the x to the tangent inverse again. I mean, we can just keep going and make it, just as ugly as we possibly could. So it just, there are really ugly functions that are very difficult to deal with, especially when we want to deal with them under differentiation or if we want to deal with them under integration. So there's a big need for taking a really ugly function and turning it to a much prettier function. And by prettier, I mean a function that behaves really well under differentiation and just as well under integration. So a recurring issue in these sections is to find, or we'll find out, build nice or pretty functions that approximate less well-behaved or well-understood functions. Why would we bother to approximate? Well, that's what I said. We want to deal with a nicer function than an uglier function, something that's easy to differentiate, easy to integrate. And polynomials form one nice family of functions. Calculus with polynomials could not be easier. It's convenient. There are only two rules. There's the power rule for differentiation and the power rule for integration. Hardly easier. So just as important, polynomial functions are easy to evaluate, even by hand or with crude technology. If I ask you to find x cubed, where x equals 3, accurate to 5 decimal places, that would be a lot easier than asking you to evaluate e to the x, where x equals 3, by hand, without any technology, accurate to 5 decimal places. So we're going to see how a polynomial can approximate another function and why we want that to happen. So here are two functions. Here's f of x equals e to the exponential function, natural exponential. We understand what it looks like in the plane. We know that it grows without bound as x gets larger and larger. As we have negative input values, the output values hover right above the x-axis, super tiny positive output values. We know it has a y-intercept point at the point 0, 1. We know it has no x-intercept points. This function never equals 0. So we know a lot about how it behaves. But what if I said I wanted you to give me f of negative 1 accurate to 5 decimal places? And I didn't give you a calculator or a computer or a CAS in order to do that. I wanted you to do it by hand. That would be really difficult to do. But let's suppose I gave you this polynomial. We're going to call it for now p sub 5 of x. You'll see the significance that the 5 has in just a little bit. So we're going to call this p sub 5 of x. It's made up of nothing but power terms. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120. Now, it might take some paper and some pencil and some time, but if I told you I wanted p sub 5 of negative 1 accurate to 5 decimal places, that's doable. It's absolutely doable, and you know enough mathematics to get it done. And it wouldn't take forever. It would take some time, but it wouldn't take forever. Where f of negative 1 might be impossible for you to do. So we are going to ask ourselves, how closely does the polynomial approximate the function near x equals 0? In other words, how closely does p sub 5 of 0 approximate f of 0? Well, this one we can do. We know that e to the 0 is 1. Everywhere there's an x over here, we're going to plug in 0. We have 1 plus 0 squared over 2, and so forth. And we see that at x equals 0, p sub 5 of 0 is equivalent to f of 0. It is 100% accurate to infinitely many decimal places. Well, that's pretty handy. But the further and further and further we get away from 0, let's say at x equal negative 1 or at x equal 2, how closely does the polynomial approximate the function? So let's take a look and see. Here's f of negative 1. So it's e to the negative 1, or 1 over e to the 1. And that is approximately 0.36788. So p sub 5 of negative 1, once we plug negative 1 in and evaluate it, everywhere that there is an x, that should be negative 1, we get 0.36667. So this is accurate, if we rounded this up, it's accurate to 3 decimal places. That's pretty good. I mean, within 1/1000th of an error, p sub 5 of negative 1 acts like f of negative 1. So depending on what I'm doing with this value, if 3 decimal place accuracy is within my accepted error for whatever my boss is telling me to do or whatever's going on with this function, whatever it's modeling, p sub 5 of negative 1 is acceptable. All right? Now, let's say p sub 5 of 2. That's e squared. Here it is with 5 decimal places shown, f of 2. P sub 5 of 2 is not a great match, not super impressive, but if we were talking ballpark, it's accurate after rounding to within 1/10. So again, depending on what I'm modeling and how important it is to my work, I mean, if I'm feeding starving children, I want to be more accurate than, if I'm figuring batting averages. It's still a respectable approximation. So how did we come up with this polynomial, this 5th degree polynomial, that acts like the function e to the x so well? It acts just like it at 0, and the further I get away from 0, it acts less and less and less like it. I mean, at 0, they are equal. It is an excellent approximation. When I come over here to negative 1, we're accurate to 3 decimal places. When I come over here to positive 2, we're still accurate to 1 decimal place. Still respectable. Don't know how useful, but still respectable. So finding p sub 5 of negative 1 and p sub 5 of 2 only required arithmetic. We could do that without any help whatsoever. However, finding f of negative 1 and f of 2, if we want any accuracy at all, we need some help with a calculator, computer, something. So we're going to see how p sub 5 was chosen, or technically built, to match our function f so closely. And again, when we loop back around at the end of this whole series section, we'll see why these approximating polynomials are so helpful and what they have to do with our series work. All right, so here's why p sub 5 of x is such a good approximating polynomial for f of x. And that's because we built it in such a way that we made sure that the first 5 derivatives of both functions were equal. And we did that near a specific x value. Here we did it near x equals 0. That's why the closer and closer and closer to x equals 0, the more and more and more those two functions behave the same. We planned it that way. The output of f at 0, we planned to be the same as the output of p sub 5 of 0. Then we took the derivative of f and evaluated it at 0 and made sure that that was equal to the derivative of our polynomial at 0. And we kept that up. We made sure their second derivatives at 0 were equal, their third derivatives at 0 were equal, all the way up to the 5th derivative. Now, that's important. This forces some like behavior in our function at x equals 0. It says that in the plane at x equals 0, wherever we are, that the function and the polynomial share the same point. This is the same output. We force that to happen, and I'll show you here in a little bit how we force that to happen. This says that at x equals 0, they had the same slope. Same slope. This says that at x equals 0, they had the same concavity. Do you see what we're forcing to happen here? We have the same output, the same slope, the same concavity. Here, if we were in position, velocity, and acceleration, we would say it was the same jerk. But basically what we're going to say for these higher order derivatives is we are bending and twisting the polynomial to mimic the behavior of the function. And we'll see in a little bit how we do that, what that looks like, and why it's important. And remember, fundamentally underneath it all, we're after a polynomial function that will behave in the plane, algebraically, under calculus, whatever mathematics we want to do, very near some value. Here we're near x equals 0. We're after a polynomial that will mimic the behavior of that function to whatever degree accuracy gives us an acceptable amount of error. That fundamentally are what these polynomials are all about. Why polynomials? Because they're easy to do math on. They're easy to evaluate by hand. They're easy to do differentiation, integration, you name it. So we want to mimic these functions with polynomials. So I'm going to stop here on this video and we'll pick this lesson up in the next video. So look for that.